The title of my talk is on space infrastructure and data products for meteorological services. I will talk about the satellite systems that we have presently in India, or we had in the past, or some other satellite missions which are already approved and going to be launched very soon. I will also talk about what are the geophysical parameters of meteorological interest that we derive from these satellites, and how they are available and where they are available, what kind of data products are available, and where they are available. So I will go through my talk now. Yeah. The first question arises that why do we need the meteorological satellites? The answer is that the satellites have very large and uniform coverage, unlike the surface observations. For example, if you have the weather station, it is only giving the weather information of that particular point. But from the satellite, we have very large coverage and uniform coverage because satellite resolution is known to us, and we have the value parameter values in that resolution. Then we have the continuous coverage over any evolving system, like for example the cyclone or hurricane. You can continuously monitor it and see that in which direction it is moving and how it is moving and how it is evolving. Then you have the coverage over very inaccessible areas. For example, in a difficult terrain, over say a mountainous region, or even over the oceans where we hardly have the surface observations. Then we have the near real-time availability. For many applications, we require the near real-time availability of the data. For example, the weather forecasters, they require the data immediately after it is received by us because they put it in their numerical weather prediction models to give the prediction of what the weather is going to be in next say 6 hours or 12 hours or 24 hours or in a day or two or three. And the satellite, maintaining the satellite is much cheaper compared to the network if you have the similar ground network everywhere. For example, if you put lot many weather stations and to have the coverage similar to that of the satellite, it requires lots of money. So from that point of view also it is very important. Then you have the continuous data availability in all weather conditions, in the severe weather conditions also, because satellite looks from the space. Sometimes what happens, there is suppose heavy rain and the area is flooded, then that station may not be accessible to the human for getting the data. But satellites have no such problem. You have the data availability in all weather conditions. So uh, these are the advantages of having the satellites for the meteorological applications. Now, what are the meteorological applications one can do or think of using the satellite data? One is the nowcasting for aviation and also for the severe weather conditions, for example, the cloudburst or the intense rain events. So for that, you one need to do the nowcasting. Nowcasting means what is going to happen in next, say, example, 3 hours to 6 hour time, say up to 6 hours of time. What is going to happen? We are trying to predict that situation using satellite data. So it is used for the nowcasting. It is used for the numerical weather prediction model because the numerical weather prediction models, their prediction depends upon the present state of the atmosphere and how it evolves. That evolving that is solved through the numerical equations. But the defining the present state is very important. It is called the initial value problem. So initial state of the atmosphere is not if not the well defined, then you will not have a good prediction from the numerical weather prediction model. So it helps defining the initial state of the weather. Then comes the seasonal forecast, say for for what is going to happen in the next month, or say what is going to happen in the next 3 months. For example, we have the seasonal forecast for the monsoon this year, how the monsoon is going to behave this year. So for that also, it is required. It is required for the extreme events, prediction of the extreme events. Apart from that, these observations are also needed for various other applications that includes the climate research and also many other such things like hurricane or the cyclone study, movement of the cyclone, like that. So there are many applications. In this table, I have given in the second column the parameter. What are the parameters that can be derived from the satellites, and what are their applications, where they have the applications. So some of the parameters, this is not the complete list, but this list gives you some idea that where they can be useful. For example, the clear sky radiances from the satellites like INSAT can be used for numerical weather prediction model. They go as input to the numerical weather prediction model for improving the weather forecast. Atmospheric temperature humidity profile, that goes also for NWP, that is numerical weather prediction for nowcasting, cyclone, thunderstorms studies, etc. Similarly, there are many such atmospheric parameters. They are derived from the satellite and they go into the various numerical or the statistical models for predicting the weather. So this is one table which I just wanted to show you to have some feeling that how, where and how we are using the satellite data for various applications. Now, little bit of I will go a little bit into the basics. Satellite observations mostly for meteorology and oceanography and otherwise also. We use a few wavelengths or say spectral wavelengths for this purpose. Usually we use the visible, near infrared and the microwave ranging of the electromagnetic spectrum for doing the measurement, satellite based observations. Why we do that? Why not in the other part of the electromagnetic spectrum? The reason is that in this part you can see this figure here. The gray part, this is showing the atmospheric transmittance. This is the atmospheric transmittance, and this is the wavelength or the frequency in the electromagnetic spectrum. This is the ultraviolet regime, this is the visible, this is near infrared, this is thermal infrared, this is the microwave part of the electromagnetic spectrum. You see, this gray area shows the region where there is absorption in the atmosphere. So in those regions, you will not, radiances does not reach to the satellite because of the high atmospheric absorption. So those regions cannot be used for any meaningful study of the atmosphere. But in certain regions, you can see that there are regions where you have this transmittance almost 100%. Those regions are used for the satellite remote sensing, and within those regions also there are certain bands, absorption bands of various atmospheric constituents, and they are used for deriving those atmospheric constituents from the satellite data. For example, water vapor have in the visible band the absorption bands at absorption lines at 0.7 to 0.82 and so on up to 6.3 micrometer. Similarly, CO2 has these absorption lines I have written here. They have 1.4, 1.6, 2, 2.7, 4.2, 9.4, 10.1, 15 micrometer. Similarly, ozone, oxygen, nitrous oxide, methane, and carbon monoxide, all these gases have their absorption bands at certain frequencies or certain wavelengths. And this part is the microwave. Microwave, we have the absorption lines only of water vapor and the oxygen. There are only two absorption lines. One is the water vapor, another is oxygen. They are at 22.235 gigahertz and 121.31 gigahertz for H2O water vapor. And for oxygen, there is actually a continuum of absorption, say from 54 gigahertz to 64 gigahertz, and another as 118.75 gigahertz. So what are the sensors that we have on satellites? They either work on the visible, near infrared or thermal infrared or microwave part of the electromagnetic spectrum. Because in other parts there is a strong in other parts there is a strong absorption, or wherever there is a strong absorption of the atmosphere for these wavelengths, there we cannot operate the satellite instruments. So this is just for the basics. Now, from the satellites, particularly for the meteorology and oceanography, there are two types of sensors. One set of sensors are called the passive. Another set of sensors are called active. Passive sensors are those which receive the energy which is reflected from the atmosphere or the earth and reaching to the satellite. This is the sun energy which is reflected from the surface or the earth and reaching to the satellite, or scattered from the surface and reaching to the satellite, or emitted from the atmosphere or the surface of the earth and reaching to the satellite. These type of sensors don't carry their own source of energy. They only receive the energy, which is basically the emitted energy from the below or reflected solar energy from the below. Another set of sensors are active. They carry their own source of energy, and they measure the what is the back scattered power from the below. They measure that amount of the power, and they are essentially the radar systems in the microwave or the lidar systems in the optical part of the electromagnetic spectrum. Then sensors may be imaging type or non-imaging type. All of you might have seen the cloud images on TV. They are imaging type of, but there are many other instruments which are non-imaging. Basically, any two-dimensional data set can be viewed as an image. But if the data is one dimensional, or it's not distributed in a very regular fashion, it is scattered, or measurements are scattered all over, you cannot form the image out of it. And such is the instrument which provides such kind of measurements are non-imaging type of. There are some examples of it. Imaging instruments in the passive category are radiometers. They are called radiometers. Non-imaging, there are many instruments. One example is given here of GNSS receivers for atmospheric sounding. GNSS is Global Navigation Satellite System. I will come to that later part of my presentation. Then we have from the active, we have the centrifugal aperture radar and the scatterometer. They are imaging type of, and they are essentially the radar system. And another non-imaging is, for example, is the altimeter. That is also basically in a radar system, but operates in a different principle. So, and then another important aspect of the satellite measurement is the orbit. Basically, there can be any type of orbit depending upon the requirement. Requirement means for a particular purpose or applications, what is the repetitivity of the observation is required. Whether you require the observations every 5 hours or every 10 hours, or one observation in a day, or two observations in a day, or say 5 observations in a day, or alternate days, like that. So it all depends upon that. If you want the more observations, you may have to put satellite accordingly, place satellite accordingly in a particular inclination angle. Latitude and inclination angle. But what happens if you have the more observations in a particular area, then you may not have the global observations. You will certainly have the more you can have the more observation in a certain area, but not every area. But more commonly there are two types of orbits. One is called the geostationary orbit, another is the polar orbit. Example of the geostationary orbit is given here. Here, satellite and the Earth, they both move in the, they have the same angular velocity. So the satellite appears to be stationary with respect to the Earth. And this is the geostationary orbit. And for INSAT, for example, our INSAT series of satellite, inside 3D or 3DR, they are present. They are placed in the geostationary orbit, and they continuously observe over a certain part of the Earth. So we have the INSAT 3D, 3DR. They are placed over India, and they continuously observe over the India, and they can provide the observations every 30 minutes. And then we have another type of orbits which is shown here. This is the polar orbit satellite, and they are generally the sun synchronous. Sun synchronous means, the orbit is made such a way that there's the angle between satellite and any location on the Earth and the sun remains constant when they move. The advantage of this kind of satellite is that, whenever it passes over a certain region, the illumination conditions never change, because Earth is moving and satellite is also moving. They are arranged in such a way that the illumination conditions at any location remain same. So you have, same type of observations there, and whatever variations you will see in the satellite images, they are due to some changes in the atmosphere or the surface, not because of the sun. So they are different. This is different type of orbit. So little bit, I felt that you should have a little bit of idea about what are the satellite orbits and what kind of instruments we use. Many of you may be aware of it, but I felt that many of you may be, they are new to the subject and may not be knowing it. So what I have spoken about is that we have different sensors working in the visible and the IR part of the electromagnetic spectrum and the microwave part of the electromagnetic spectrum. What the visible and IR instruments can sense, what are passive instruments can sense, what the parameters you can get from them. Satellites, they only measure radiances. They do not measure any parameter as such. For example, they do not measure the precipitation or rainfall or sea surface temperature. They do not directly measure it. They only provide us the radiances. Then we here use that data to derive the certain atmospheric parameters. And from the visible and IR sensors, what are the parameters can be derived? I have listed here. You can see them. They are some of them I have listed here, which are of meteorological interest. Otherwise, there are many more parameters which can be derived from it. Precipitation means rainfall can be derived from it. Atmospheric motion vectors, they are basically, you can call them the winds, and they are actually called atmospheric motion vectors, because if you have the two consecutive images of the from the satellite, and you try to correlate them, then you will see that you can figure out that in which direction the clouds are moving. So if you can figure out that in which direction clouds are moving, you can draw a vector, a motion vector to it, and because they are basically due to the movement of the atmosphere or the clouds, they are called the atmospheric motion vectors. Then sea surface temperature, land surface temperatures, cloud types, and cloud macrophysics can be derived from the visible and IR sensors. Then outgoing long wave radiation, fire, smoke, aerosols, upper tropospheric humidity, fog, potential transpiration, land surface insolation, vertical temperature profile, humidity profile, ozone profile, trace gases, and cloud lightning, etc. This is not the complete list. There are many more parameters which can be derived, but they are the basic parameters of the meteorological interest. In fact, we are providing about 40 parameters from INSAT to the user community, and they are regularly being retrieved and being provided through our website, and also from IMD, Indian Meteorology Department's website. And then visible, what the active sensors in the visible and IR can provide, they are basically the LiDAR systems. They can provide the wind speed and the direction in the atmosphere at different layers of the atmosphere. They can also provide the temperature, pressure, and density of the trace gases. They can also provide the aerosols and the cloud parameters. So these are some of the parameters that the active instruments can provide. Presently, India doesn't have any active instrument in the visible IR part of the electromagnetic spectrum working on any of the satellites. Now, what the microwave can sense? So microwave, as I said, that there are passive instruments and the active instruments. Passive instruments are called the radiometers or the sounders. They can provide the number of geophysical parameters I have listed here. The green one which you see here are actually of the meteorological interest. Blue one I have listed, but they are not typically meteorological parameters. They are oceanographic parameters or parameter of other geophysical parameters which are not directly related to the meteorology. For example, the passive instrument, if you see, then we have the surface wind, SST, sea surface temperature, soil moisture, snow cover. This I have listed here. Then there are the active sensors. We have the altimeter instrument that can provide the many parameters of the oceanography, interest of the oceanographers, but it can also provide the ocean surface wind speed. That is of the interest of the meteorologist. Synthetic aperture radar that has mostly the oceanographic applications apart from the land applications, but they have mostly the oceanographic applications. It can be used for few meteorological studies like studying the atmospheric fronts or say cyclone like that, but not very much useful for meteorology, but still we make some uses of it. A scatterometer is a very useful instrument that can provide the wind vector. Actually, the in the wind drives the atmosphere, and it is a very important parameter for numerical weather prediction models. And scatterometer is one instrument that can provide the wind vector over the oceans. It can provide both two component U and V components of they are orthogonal components of the winds, and one can derive with the scatterometer. Then precipitation radar that can provide the vertical profile of the precipitation. That means it can provide that where rain, not only the rainfall at the surface, it can also provide that how much rainfall is falling at different layers of the atmosphere in the vertical. That is very important because when the rain starts falling, it releases the latent heat in the atmosphere. That latent heat is a very important component for driving the atmosphere, particularly the tropical atmosphere. And if you don't have the measurement of precipitation at different layers of the atmosphere in the vertical, it is very difficult to know that how much energy is released in the vertical. The GNS refractometry and GNS refractometry and refractometry are they are relatively newer concept. I will come to that in the later part of my presentation, and they can provide the temperature and the relative humidity profiles, and also the ocean surface winds. India has a series of meteorological satellites right from 1982 till present. Presently, we have the INSAT 3D and 3DR operational, and we are going to have another 3DS in near future. INSAT 3D and 3DR are similar type of systems, and 3DS is also going to be similar to them. Then we are going to have a GI-SAT I will come to that. What are the instrument it is carrying, and what are the parameters that can provide. I will come to that in later part. Then we are also defining the INSAT 4 series that is being presently defined, and that will be coming later in 2024 or beyond. Indian Meteorological Society, which I was talking about in this slide, was that satellites which are in the geostationary orbit. Apart from having satellites in geostationary orbit, we also operate many satellites in the low Earth orbits. And we started the first satellite we launched the first satellite in 1979. That was called the Bhaskara 1, that carried a microwave radiometer Samir. That worked in two spectral, that had the two channels, 18 gigahertz and 21 gigahertz. And it also had a TV camera, two TV cameras at that time in 1979. And presently we are going to have OceanSat 3 in near future, maybe later this year, and it will be carrying a scatterometer, a scatterometer that can provide ocean surface wind speed, a wind vector. That means both the U and V components of the wind. And it will also be carrying an instrument called the ocean color monitor that is useful for the biological oceanography, and it will be also carrying a SSTM, that is the sea surface temperature monitor, that will provide the sea surface temperature over the global oceans. It is going to be launched very soon. Now coming to the basic of the satellite imageries. In the satellite imageries, what we try to figure out that what we see in the satellite images, that is actually the visible manifestation of that different atmospheric processes. And if you see the clouds, you can see the cloud, you can see the surface, and satellite images taken different parts, different instruments working different part of the electromagnetic spectrum give different information. I will come to that in my next slide. For example, this is a visible image. What the visible image shows, it shows the reflectance. It is showing the reflectance from the sea, land, and the cloud. You see, area which is more reflective will look brighter, which is the less reflective will look, darker. And this is reflecting the solar energy. And this is similar to what we see from our eyes. This visible band image means it is working in the visible part of the electromagnetic spectrum, that is 0.4 to 0.7 micrometer wavelength. So this is how you will see in the visible image. If you see the thermal infrared image, what the thermal infrared image will show? Thermal infrared image, actually, if you have studied the Planck's law and other laws which are derived from that, the Stephen Boltzmann law says that a warmer body emits more and a cooler body emits less of the energy. And in the thermal infrared image, in the thermal infrared part of the spectrum, solar energy, reflected solar energy is almost zero. It is not there at all, or say it is negligible. What energy it receives is the emitted energy from, and that emitted energy is received by the satellite. And here what it shows, it is showing the area which is cooler, it will show it darker, and the region which are warmer, it will show that as darker. But actually, when we see the satellite image, it looks different. Here, cloud which are colder, they appear brighter, whereas the surface which is actually warmer, actually appearing darker. That is because of some convention. This image is actually reverted. The area which should appear brighter in the processing level, at the when we do process it, we revert it. The darker part is shown as the brighter, and brighter is shown as darker. This is a convention only. It has got nothing to do with the quality of image or the retrieval of the parameters and all. This is a convention so that it appears more like visible image. Then water vapor channel image, that is actually working at the water vapor, close to the water vapor absorption band at 6.7 micrometer. Here, here also the reflected radiances are almost negligible. All solar reflected radiances are almost negligible. What you get is only the emitted from the surface of the earth or from the atmosphere. But because you are working in the close to the or at the absorption band of the water vapor, the radiances in this wavelength which are coming from the surface are absorbed by the intervening atmosphere. You will see only from what is appearing from the top of the atmosphere. So what it shows you is only the water vapor plumes in the atmosphere. It only shows you that where the water vapor is more and where it is less, and how the water vapor is moving. Then in the microwave part, in the microwave, this is 85 gigahertz brightness temperature from the satellite. In the 85 gigahertz brighter temperature, what you see the clouds as very cold. Actually, in the microwave, if you are working at the low frequency, say 19 gigahertz or 10 gigahertz, you have here also the reflected solar reflected radiances are negligible, almost you can assume they are zero. And what you get only the emitted radiances from the surface or from the atmosphere. And here what happens at the very low frequency, they interact with the clouds and the precipitation. If the cloud and the precipitation are not present, then they are transparent to the atmosphere. But if they are present, then they interact with them. Interaction with the precipitation is more, and that is significant, and that depends upon the wavelength at which it is being observed, because the scattering and the emission theory, that depends upon the particle size and the wavelength, interacting wavelength. So what happens at the low frequency, say 10 gigahertz or 19 gigahertz, you will have the emission dominating. But as you will go to the 85 gigahertz, you have the scattering dominating because of the scattering and the absorption theories in the physics. So as a result of which, at the 85 gigahertz, what you see the brighter part is the more scattering, and this scattering comes from the ice on the top of the cloud. So they may be possibly the convective clouds and maybe giving the more rain in that region. So this has a different interpretation vis-a-vis that you have seen in the thermal infrared or water vapor or the visible part of the spectrum. This is the INSAT 3DR. You all might be knowing that it has got a 6-channel imager and 19-channel sounders. And this we actually retrieved lot many parameters from it, and a list of the parameters is given here. In my previous slide also I talked about it, and we give about 40 parameters from the INSAT to the IMD on real-time basis. And we also host those parameters on our website for the users. This is the example of some of the parameters. This is the temperature and the humidity profile. The INSAT can provide the temperature and the humidity profile in the atmosphere. It can provide the precipitation. It can provide the SST and many more parameters. It's just an example. Now coming to passive macroradiometers, we work on certain frequencies in the passive microwave region. The reason is that the frequency allocation in the microwave is done by the International Telecommunication Union for different purposes. So we have to work in those frequency bands, wavelength bands, which are allotted for the remote sensing purpose, because these frequencies are also shared for the communication and many other purposes. So we work with certain frequencies. These are some of the common frequencies for the passive macroradiometers, and what are the parameters we can derive from them. They are also listed here. India had a megatropic satellite. It was launched on 12th October 2011. It was an Indo-French joint mission, and it carried many instruments. One is called the Saphir, that is the microwave sounder, a kind of radiometer, and that was capable of providing the humidity profile in the atmosphere. That means the vertical distribution of the humidity at 6 broad vertical levels, and it had 6 channels. Channels, and all channels were very close to the water vapor absorption line at 183.31 gigahertz. You can see the frequency channels here in this, and all channels were H polarized, horizontal polarized. And we have another instrument called microwave instrument called a Madras, and that instrument had 5 frequencies, 18.7 to 157 gigahertz, and polarization was V and H. For most of the V means vertical and H means horizontal polarization for all the channels except for the 23.8 gigahertz, which had only the V polarization. It also had one instrument called a SCARAP, That was for measuring the fluxes. That means how much energy leaving the earth, or in the short wave or the long wave. And scrap provided the estimation of that energy which is leaving the earth. So it provided the outgoing fluxes at the top of the atmosphere, having several spectral bands in the visible, solar, and the thermal infrared part of the electromagnetic spectrum. It provided a number of parameters like water vapor, clouds, cloud condensed water, precipitation, evaporation, etc. MT Madras has given as I said, cloud liquid water, wind speed, and total precipitable water over the oceans, and it is showing the distribution, global distribution from it, and it is compared with the similar product from the other NASA instruments. Then the Madras was also used for measuring the rainfall, and it gave the very good estimation of rainfall. Unfortunately, the Madras worked only for about 14 months. Then it has some technical problem. It developed an anomaly and it was abandoned. But other instruments worked till recently, and say about 1 month back only, or 1 or 2 months back, till 1 or 2 months back they were working, but now they are no more working. And megatropic Saphir provided, as I said, it provided the humidity profile at 6 vertical levels, and this is one example of it. At 6 levels, it is being provided, and it is given to the users for various applications, particularly for weather prediction purpose. And once the Madras instrument failed, we tried to retrieve the rainfall from the Saphir, another instrument on megatropics, and we provided the precipitation from the Saphir. It was also hosted on our website for the users. As I said, MT scrap that provided the long wave fluxes and the short wave fluxes at the top of the atmosphere, how much energy is living in the long wave and how much energy is living in the short wave. That was determined, and we provided it to the users from our site. We also had a satellite mission called the Saral Altica. That was also ISRO and CNES joint altimeter mission. CNES is the French space agency, and altimeter principle as such is very very simple. It sends a pulse from the satellite and measures the distance. And all of you in the physics background know that it is so simple to measure the distance, because you know the speed of the electromagnetic waves, 3 into 10 to the power 8 meter per second. So it is not a big deal. But it is really difficult to do it when you have to measure with an accuracy of 1 centimeter. If you want to make the measurement of 1 centimeter, then if you do a little bit of calculations, you will find out that you have to measure the time with the accuracy of 30 picosecond. There the technology comes, and the importance of the technology comes. You have to measure, with such an accuracy, time accuracy, that you can able to measure the return pulse with 30 picosecond accuracy. And this is really a difficult job, but it is done using some technological advancements. And Saral Altica was a successful mission. It is still on. It provided the sea surface height and the significant wave height over the oceans. Apart from that, for meteorological interest, it provided the wind speed over the oceans. And sea surface height over the ocean is very very important, because once you know the sea surface height, change from the earlier measurement, that produces the pressure gradient force, and from the pressure gradient force you can derive the currents. They are called geostrophic currents in our language, meteorology and oceanography language. They are called geostrophic currents. So this is how it worked, and this satellite is still working. Then we have the SCAT-SAT scatometer, and SCAT-SAT scatometer is, as I said, it provides the wind vector measurements over the oceans. It worked at a frequency of 13.51 gigahertz. It is radar systems. There are actually 2 antennas. They are swapping the surface below it, and drawing 2 circles like this, as shown in the figure. The inner circle is one and outer circle is one. Inner circle is having, HH polarized radiances, and outer is the VV. So what happens? HH means H polarized wave is sent and H polarized is received. VV means V polarized is sent and V polarized is received. And once it sweeps these circles and it moves on. So you can imagine that in each part of the Earth, or each part of its coverage area, you will have the four observations. One, you will have the HH. One, you will have the VV. Another, you will have the forward-looking direction. Another, you have the after-looking direction, and you have measurement at two different incidence angles as well. So with the four measurements, they are required to remove the wind direction measurement. And wind direction has some ambiguity in the measurement if you have only one or two measurements, but if you have the four measurements, you can remove those ambiguity and get a very more accurate wind speed and direction measurements. This is how the spectrometer works, and a spectrometer wind products were provided to global users. They are in real time. We have provided to the NASA, NOAA, as well as to the EUMETSAT, and another countries also received this data on real time with us under some MOU, memorandum understanding with those countries. Synthetic pulse radar I will just skip because this is not so useful for the meteorological applications. In future, we are going to have GISAT, a satellite which will change the entire direction in which we do the measurements. It will have the instruments. They will have a number of channels, and they are called hyperspectral channels. And those hyperspectral channels will have a number of channels, say about 60, or in some cases it is 60, in some cases it is 150. And once you have those number of channels, you can have many measurements of the atmospheric constituents, because many atmospheric constituents having the absorption lines, very weak absorption lines, and those absorption lines are we are not able to use when you are using the broad channel. But if you have very narrow channels and many channels, you will able to capture the energy, change in energy because of those absorption lines, as that energy is received by the satellite, and you can have the measurement of those atmospheric constituents. And we are also going to have the OceanSat 3 in the future, very near future. As I said earlier, it will have the spectrometer, SSTM and OCM. I have described it earlier. It will give number of parameters. Many parameters are not of the meteorological importance, but those which are I have written with the red and in bold, they are of meteorological importance, and they will be provided to the users. Now, so what are the satellite meteor products for researchers? We have, satellite data. When we talk of the satellite data, we say it is L1 data, L2 data, L3 data, L4 data. What is the L1 data? L1 data is actually the basic data which is provided to the users. They are the satellite images. They may be the brightness temperature, maybe reflectivity images, or maybe radar backscattering coefficient images, etc. And L2 data is those which are actually the geophysical parameters which are retrieved from the satellite data, from the L1 data. So that may be, like sea surface temperature or wind vector or say rainfall. They are called the L2 data. L3 data are those which are actually gridded in space and time. L2 data is provided on the satellite swath itself. But in L3 data, they are gridded for making the map, weekly map, or say daily map, or say monthly map, etc. L4 data is one which, when we have some value addition to the data. For example, we use the numerical weather prediction based analyzed winds, and we merged it with the spectrometer winds, and we generated a product for the global wind. And that when you add something to it, which may or may not be of the satellite, which may or may not be of satellite derived, then that is called, we call that the L4 product. These are L1, L2, L3, L4 product from the Indian missions are available from our MOSTEC site. And apart from that, we also provide lot many other services from our MOSTEC site. For example, we use the satellite data and do lot many experiments for improving the weather prediction. So we provide the numerical weather prediction forecast from the model. We provide the different forecasts, for example, temperature, relative humidity, cloud, wind, rain. Rain 24-hour accumulation, 3-hour accumulation we provide using from the NWP numerical weather prediction models using the satellite data. Our emphasis is to use the satellite data and show that satellite data is useful for the NWP purpose. And we provide all this through our website mostec.gov.in. And we also provide the climate model based predictions. For example, we have provided the monsoon prediction for this year, weekly prediction, and also the seasonal predictions we provide from our website. We also provide the image based forecast. Most of the nowcasting, as I said, is weather outlook in next 6 hours. That is called the nowcasting, and that is mostly the image based or statistical tools are used to do that, and we do it in the real time. And a lot many such parameters or products we provide, like intense rain or cloud burst, etc., for the country. Other applications we also provide, cyclone forecast, cyclone intensity forecast, cyclone intensity forecast, its track forecast, its landfall, etc. We also provide the energy forecast from our website. These are all satellite driven, or mostly with the satellite data and with the methods developed by us or techniques developed by us. Then ISRO also operates 3 radars. One is they are Doppler weather radars. One is the Sriharikota, and one is at Cherrapunji. We provide data from these 3 radars also through our website. MOSTEC. This is the MOSTEC website. Any one of you can, interested, can just request for the registration. Once you are registered, you can download the data. The data is available both in the image form as well as the digital form. If you have the digital data, you can use it for your, developing newer applications and all. We provide it for free. The summary of my presentation is that what I have covered here. I have covered the need for satellite observation in meteorology. Number 2, the Indian meteor satellites. I have talked about them. What were the Indian meteor satellites? Which were past satellite, present satellite, and which are proposed or approved. Then approved by the government. Then I have also talked about different type of observations and the retrieve parameters from them. I have also talked about the brief introduction of the available meteorological satellite products and services using the satellite observations. And the MOSTEC, I also talked about the MOSTEC, that is actually Meteorology and Oceanography Satellite Data Archival Center. MOSTEC stands for Meteorology and Oceanography Satellite Data Archival Center. You can just use the mostec.gov.in, and you can view many products, and if you want to download the digital data, you can register and you can download the data and use it.